By the end of this lesson, you should be able to solve equations with complex numbers by equating real and imaginary parts. Let's see what we mean by real and imaginary parts. If we take a complex number 3 minus 4i, it has a real part that's equal to 3 and an imaginary part that is equal to minus 4i, which we would just say as minus 4. In general, if we had a complex number, that would be z equal to a plus bi, so the real part there is a and the imaginary part is bi or just b. And then if we had two equations, two expressions that we set equal to each other, so if we had a plus bi equal to c plus di, then we can equate the real parts. That means that we have a is equal to c, and we can equate the imaginary parts, which means that b is equal to d. Okay, this is an example for your notebook. Let's have a look at how we would solve the equation 3z plus 2i equal to z star minus 6. Firstly, we need to understand what that z star means. So if we see z, then we can rewrite that as a plus bi, and z star is the complex conjugate of z, which is a minus bi. So we have negated the sign of the imaginary part there. Now we can substitute these two in. So where we see z and z star here, we can substitute in the a plus bi and the a minus bi, and then we can start to solve this. So if we multiply out both sides to remove those brackets, we can then take a look at the real parts and imaginary parts separately. So looking just at the real parts, that's anything without an I, so we have 3a, a, and the minus 6. Which we can then simplify to a is equal to minus 3. Looking at the imaginary parts, those are the bits with the i's attached there, 3bi, 2i, and minus bi. And we can again rearrange this so we have b is equal to minus 0.5. And to finish this question off, we just need to write what the solution is for that complex number. So z is equal to minus 3 minus 0.5i. Okay, another one for your notebook now. So solve the equation a plus 2i all squared is equal to b plus 12i. Let's multiply out that left-hand side. So a plus 2i multiplied by a plus 2i will give us a squared plus 2ai plus 2ai plus 4i squared. This will simplify to 4ai, and then here the 4i squared will become minus 4 when we replace I squared for minus 1. So this is now equal to b plus 12i, and we can begin to look at the real and imaginary parts. So looking at the real, we have a squared minus 4 on the left and b on the right. At this point we can't solve this, we have two unknowns and one equation. So we need to take a look at the imaginary equation as well. So we have 4a on the left and we have 12 on the right. One equation, one unknown. A is equal to 3. Okay, we can now substitute the a equal to 3 into the real equation. And so this becomes 3 squared minus 4 is equal to b. And therefore b will be equal to 9 take away 4, which is 5. So our answer here, a is equal to 3 and b is equal to 5. Let's have a look at another one for your notebook. Here we've got z squared is equal to 8 minus 6i. To begin with, we know that z is equal to a plus bi, and we define a and b to be real numbers. Substituting in a plus bi then gives us a plus bi multiplied by a plus bi, so this is the z squared. So the left hand side, if we multiply that out, this will give us a squared plus 2 abi plus bi all squared, which then will simplify to a squared plus 2 abi minus b squared, and that is equal to the 8 minus 6i. If we equate the real and imaginary parts, so we have a squared minus b squared is equal to 8, and we have 2ab is equal to minus 6. We then solve these simultaneously. Starting with the imaginary equation, if I rearrange this, so I have a equal to, that would be equal to minus 6 divided by 2b, which gives me minus 3 over b. I then substitute this into the real equation, so I have minus 3 over b all squared, subtract b squared, and that equals 8. Multiplying out gives me 9 over b squared, take b squared is equal to 8. Continuing now, in order to simplify this, we need to get rid of this divide by b squared down here. In order to do that, we need to multiply each of these terms by b squared. So multiply through by b squared, this is 9 minus b to the power 4 is equal to 8b squared. And rearranging this gives us b to the power 4 plus 8b squared, subtract 9. And this will nicely factorise. So we have b squared plus 9 and b squared minus 1 equals 0. And solving each of these, so we have b squared plus 9 is equal to 0 and b squared minus 1 is equal to 0. Now the equation on the left, b squared will be equal to minus 9. We stop at this point. Since we defined a and b to be in R, if we continue to solve b squared is equal to minus 1, that would mean that b would be a complex number. Therefore, there are no solutions to this equation. Continuing with the equation then on the right, so we have b squared is equal to 1, which implies that b will be equal to plus or minus the square root of 1, which is 1. Substituting this back into one of the original equations then, I'm going to take this equation here, so a is equal to minus 3b. So a is equal to minus 3 over 1, the positive, and a is equal to minus 3 over minus 1. Simplifying, a will be equal to minus 3 when b is equal to 1, and a will be equal to 3 when b is equal to minus 1. Let's take a look at another example. Find the square roots of the complex number minus 5 plus 12i. So the square roots of minus 5 plus 12i, the answer would be in the form a plus bi, the general complex number, and if we square both sides, we are looking to solve this equation, which is very similar to the equation on the previous slide. The left-hand side, you should be familiar with multiplying this out now. This gives us a squared plus 2abi minus b squared. So I've already substituted in the minus 1 for I squared there. And equating the real and the imaginary parts, we have minus 5 is equal to a squared plus, minus b squared, and 12 is equal to 2ab. So we are solving these simultaneously. Taking a look at the imaginary equation, rewriting a equal to, so we have 12 divided by 2b, which is 6 over b, and substituting in to the real equation, have minus 5 is equal to a squared, which is 6 over b all squared, subtract b squared. Right hand side here, 36 over b squared minus b squared. And again, similar to the last example, we want to get rid of the divide by b squared. So I'm going to multiply each term by b squared. Let's write that over back at the top. So multiplying each term by b squared, we have minus 5 b squared is equal to 36 minus b to the power 4. Now I'm going to take the b to the power 4 to the left hand side in the 36 so that the b to the power 4 is positive. That gives us b to the power 4 minus 5b squared minus 36 equals 0. This can be factorised. So we have b squared plus 4 and b squared minus 9 is equal to 0. And this leads us to b squared being equal to minus 4 and b squared being equal to 9. Again, we cannot solve this because a and b are defined to be real, and here b would lead to a complex number. So continuing to solve for b squared gives us b equal to plus or minus 3. Substituting this into our equation for a here, we then have a is equal to 6 over 3 and a is equal to 6 over minus 3, which is a is equal to 2 when b is equal to 3, and a is equal to minus 2 when b is equal to minus 3. So we then have two complex numbers, z is equal to 2 plus 3i, and z is equal to minus 2 minus 3i. Please turn to exercise 1A on page 5 and 6 and complete questions 8 to 16.